Okay, welcome to today's video. Today we're going to continue looking at different tools or rules that we have to tackle more complicated functions, finding the derivatives of more complicated functions. In the last video, we looked at how to take the derivative of something where you have two functions multiplied together or two functions divided. Well, in this case, we're going to look at functions inside of other functions or composition of functions. So, for example, functions like this, the square root of x squared plus 11. This is a composition of functions because you have this function x squared plus 11. All of that is underneath the square root. And so it's a function inside of a square root function. Okay? So how are we going to find the derivative of something like this? Well, to understand where chain rule comes from, we need to look at this in terms of Leibniz notation. Okay? Leibniz notation of a derivative. You don't need to remember the word Leibniz. Okay? I'll use it every now and then, but I'm really just talking about this notation dy over dx. If you remember, this represents derivative because this is my change in y over change in x, but it's an infinitesimally small change in y over an infinitesimally small change in x. Now, to be clear, I can also write this as the derivative of y in terms of x. That's the other way you can think about it. It's the derivative of a function y in terms of this variable x. Well, it turns out that I can rewrite this in a fairly straightforward way by just introducing a new variable. So what we're going to introduce is this middle variable u, and I can rewrite it like this: dy over du times du over dx. And these two things are equal. Hopefully we can see why they're equal, because if I wanted to simplify the right side, all I would need to do is just cancel out the du that's on top and the du that's on bottom, simplify, and you just get dy over dx. Okay? But this addition of this middle variable u allows me to play around with this. Okay? And this, in effect, is really the chain rule. Okay, we're going to look at this again in terms of function notation to make it a little more clear, but this really is the chain rule. So how does it connect to an actual example? Well, to connect this with an actual example, this middle variable u that I'm creating is what I'm really doing is I'm taking this inside function, x squared plus 11, and I'm going to go ahead and label that as u. I'm going to label that as u. So I'm going to say we're going to let u equal x squared plus 11. What does that do? That gives me a function u that's in terms of x, and it also gives me my original function. It also gives me my original function. It turns it into a function in terms of u. Okay? In fact, to put this all in terms of the same notation, what I'll do is instead of labeling this f of x, let me just label this y to make things a little clearer. That's a little bit more straightforward. So by taking x squared plus 11 and calling it u, I now have two different equations: an equation of u that's in terms of x, and an equation of y that's in terms of u. Now, if I come back to my chain rule, what this says is if I want to find the derivative of y in terms of x, I can break it up into two different derivatives. My derivative of y in terms of u, and my derivative of u in terms of x. Okay, so let's take a look at this. dy over dx equals, first off, I need dy over du. Well, what equation does that, which of my two smaller equations does that refer to? Well, I gave you a clue by drawing it in green. I want to look for my function y that's in terms of u. So what I'll do is I'll take the derivative of this function in terms of u. Okay. Well, this is just the same thing as u to the 1/2. So if I use my power rule, I get 1/2 u to the negative 1/2. Very nice. Okay, go back to my chain rule. So that takes care of this first part. But now I need to multiply it by the derivative of u in terms of x. Well, here's my u function in terms of x, so I'm just going to take the derivative of this function. and I get 2x. Right? Derivative of x squared is 2x, and then derivative of 11 is just 0. Perfect. So I can simplify this a little bit, and I get the 2 over here. Let's see. The 2 over here cancels out with that 2, and so I get x over the square root of u. Okay. The square root's in the denominator now because I have a negative 1/2 exponent. That's why the square root's now in the denominator. Okay, very nice. So I was able to get the derivative. Now we don't want to finish like this, right? Because what's my problem here? My problem is my derivative now has 2 variables in it, and I don't want 2 variables in my derivative. I want it just in terms of 1 variable. How do I get it back in terms of x? Easy. Come back to what I said u was, because now I can just replace u with the original function. And there I have my derivative. So I was able to take the derivative of a function inside of a function, a composition of functions, using this idea right here, using this chain rule idea. Okay. So let me formalize it for function notation. So if you have, let's see, if we'll have to introduce a new, we'll do h of x. If h of x is equal to some outside function with another function plugged into it, okay, a function inside of a function where g of x is your inside function, okay, there's my inside function, and there's your outside function, okay. Then the derivative of your function is equal to dy over du, represents the derivative of the outside function. So I'm going to take the derivative of the outside function, but you'll notice it ends up being in terms of u, which is the original inside function. So you keep the inside function, you keep it inside that derivative. Okay? But then you have to multiply it by the derivative of du over dx, which in this case represents the derivative of the inside function. Okay? So that's the chain rule in function notation. Okay. Let's try an example where it's actually in function notation here. Okay, so let's say I gave you f of x is equal to 3x plus 9 raised to the 4th power. Okay. Now here's why chain rule is helpful, because technically I could figure this out by expanding this out and multiplying 3x plus 9 by itself 4 times, foiling it, getting this big massive polynomial, and then I can find the derivative of the polynomial. But that's a lot of work. So the chain rule helps me take a shortcut here. Okay. So what does the chain rule tell me to do? What does this function notation rule tell me to do here? Well, it tells me to find this derivative. I'm going to take the derivative of the outside function, because remember in my definition up here, f was my outside function. So I'm going to take the derivative of my outside function. In this case, what's my outside function? My outside function is, oopsies, no, I don't want to do that. I want it in a regular pen. There we go. My outside function is x to the 4th. You okay with that? Because I have a function raised to the 4th power. Okay, so what does that give me? When I take the derivative of my outside function, I get 4x to the 3rd, but I don't want x plugged in. I want my original inside function plugged in. Look at that. Okay. So far, this piece represents this first section of the chain rule. I took the derivative of my outside function, which was x to the 4th, but instead of just but I have my inside function plugged into that derivative, okay? Because my inside function is 3x plus 9, okay? Second part, I just need to take the derivative of the inside function and multiply by that on the outside. Derivative of the inside function is just 3. Right? Because 3x plus 9 is linear, so your derivative is just your slope. Okay. Very nice. So this would be a good time to stop, pause the video, try out some problems on your homework, and then we'll come back for a more complicated example. Okay, let's look at a more complicated example here. So here I have the function g of x is equal to 2 minus x over 5 plus x all raised to the 1/2 power. And if we remember, the 1/2 power is just a square root. But this is making it a little bit easier on us so that we don't have to convert it into an exponent. Okay, this requires the chain rule because once again, I have a function inside of this exponent of 1/2 function, right? A square root function. I have a function inside of another function, okay? So to keep track, my inside function here is 2 minus x over 5 plus x. And my outside function is u to the 1/2. I like to use u as that kind of placeholder variable. Okay, so there's my outside function, u to the 1/2. Okay, so let's take the derivative. So this requires chain rule. And then if you remember, so looking back, I can look at either one of these. Okay, looking at this top example of chain rule, right? Looking at this top example of chain rule, my first thing I'm going to do is I'm going to do dy over du, which represents the overall function, the starting function, taking the derivative of that in terms of my middle variable, my u, whatever I declared u as, which really just equates to, like we said over here, it's really just taking the derivative of the outside function. Okay, so let's start by doing that. Let's take the derivative of the outside function. Well, that gives me 1/2 u to the negative 1/2. Okay, this is why I like using u, because u can help remind me that I am going to need to plug something in for that when I'm done with it. Okay, okay, well, perfect. That's not too bad. But that's just the first part. For the second part, I need to multiply this by the derivative of the inside function, right? That's what this du over dx represents. It's the derivative of whatever you called your inside function, the derivative of that in terms of x, or in this case, g prime of x. What's the derivative of my inside function? Well, this requires quotient rule, right? Because my inside function is 2 minus x over 5 plus x. This requires quotient rule because you've got a function over a function. Okay, so let's crank out quotient rule real quick. So if I'm calling this u, right, it's my inside function, so I'm calling it u prime, my derivative of the inside function is, let's see, bottom times the derivative of the top, which is just negative 1, because 2 minus x, the derivative of that is just the coefficient for the x is a negative 1, minus, keep the top, derivative of the bottom, which is just positive 1, because 5 plus x, the coefficient for the x is just a 1, all over the bottom squared. Very nice. So I can go ahead and put that back over here. I'll simplify a little bit. Turns out the x's on top cancel out, and you're just left with negative 7 over 5 plus x squared. Very nice. Okay. So not too bad, right? Even though this required quotient rule for my inside function, not too bad. Of course, we do need to clean this up. How? I need to get it all in terms of x. So, once again, the negative 1/2 you can put in the denominator as a square root. So what am I left with? I'm left with negative 7 over 2 times the square root of my inside function. Oh, goodness. Wait, I don't want to do that. That's going to get too ugly. So let me start this over. 1/2. My inside function is 2 minus x over 5 plus x, right? So I'm replacing u with what I said was my inside function. Okay? To the negative 1/2 times negative 7 over 5 plus x squared. Very nice. So all I did there, I talked about simplifying, but all I really did is I replaced u with what I said my inside function was. Now, I could keep simplifying this. I could. There's some more that I can maybe do here. But this is a little tip for when you're doing the homework. Okay, when you're working through the homework and you get to where you're going to put the answer in, take a look at any blue text that's next to that answer box. If there's no blue text telling you to simplify, you can just put it in like this. Put it in like this and you'll get full credit. Sometimes we make our mistakes when we're simplifying, and I don't want you guys to miss points just because you simplified wrong. So when in doubt, don't bother simplifying and just put it in how it is. Okay? Unless the question specifically says simplify your answer. Okay. So hopefully now you're well equipped to handle each of the homework problems. But once again, if you have any questions, let me know. Thanks, guys.